fractions tonight. Got any homework questions? Anybody got questions about anything? Doesn't even have to be that. Could be about anything. Well, it's stuff with 8.5 homework number 1. 0.5 homework number 1. Oh, that's an 11. Well, I was half right. Yeah, there we go. So number 11. Oh, there's some factoring to go with that. That's what you got. Number 11. So like I said before, 95% of these problems are all algebra. So we have get some more lights in here one of these days. Probably not there. There we go. 2x cubed minus 4x squared minus 15x plus 5. Whoops. All right, there's on the top. And the bottom of that is x squared 2x 8. X squared minus 2x minus 8. All right, so it is a polynomial over a polynomial. Oh crap, did I really assign number 11?
Yeah, you ended up having to do
yeah,
polynomial division.
Yeah, I didn't mean to assign number 11. I'm sorry, I misread the problem. But that's a good lead-in. So just throw this problem out. We're not going to bother with this. It's seriously. But actually, it's a good opening to what I'm going to talk about tonight. So this polynomial on the top has degree 3. The polynomial on the bottom has degree 2. That makes this, oh, wait a minute, let me start the recording here. So what we have here is an improper fraction. Also, what we have here is a dead marker. Hang on. I didn't mean to assign this. I guess I misread it. So just throw this homework problem out. But I was going to start out talking about this tonight anyhow for what we're doing tonight. So all the way back from grade school. So an improper fraction is something that looks like 9 over 5. That's an improper fraction because the top is bigger than the bottom. Grade school kind of thing, right? A proper fraction the top has to be smaller than the denominator. That's a proper fraction. So when we're doing partial fraction decomposition, we have to have proper fractions. And as Brandon said, the way to do this problem is to do long division, but that's just not part of what we're doing in this course here. So I apologize for throwing out number 11, so just can kind of ignore that one for now. Oops. So besides number 11, anybody got anything else? All right, so when we talk about proper fractions, when we talk about a proper fraction with an integral, for our cases, we're going to have something that looks like this on the bottom. So this is, because of that plus sign, and a is positive, this is an irreducible, quadratic. Degree 2, so this has degree 2. In order to be a proper fraction, the numerator has to be smaller than that. So the numerator has to be degree 0 or degree 1. So in order to be a proper fraction, well, a degree 1 would be a coefficient times x to the first. That's degree 1. And what's another name for a polynomial of degree 0? What's a common name for a polynomial that's degree 0?
Constant.
Yep, just a constant. Good. So when we have an integral that has a irreducible quadratic on the bottom, we have to put a possibility of something smaller on the top. Yes, and I am recording this. Now, it's possible that A could turn out to be 0. That can happen. It's possible that B can be turned out to be 0. That can happen. They can't both be 0, then you wouldn't have one at all, or they can both be not 0. So tonight we're going to see partial fractions that have an irreducible quadratic in them. And when we have that, we can break these into two. I can break this into ax over x squared plus a plus b over x squared plus a. That's how we'll break that up to do it. Now, how would you do this integral? Here's an x squared, here's an x to the first. What would be the method for doing that one? A is just a number. So this one, how would we do this integral? This would be that would be a u substitution problem. And it's going to end up being 1/2 the ln of the bottom. That's what's going to happen. So a lot of these things, you can jump right to the answer. In the case where we have something that looks like this, a constant on top, and x squared plus a number, this integral, when we have that, that's going to turn out to be a arctangent. And I'm going to show you how to do an arctangent integral just by looking at it. You just look at it and you write the answer down. I want to go through that first. It'll make our lives easier. Okay, so we have an integral that looks like this. I'm just going to put a 1 on top. It doesn't matter, any constant. X squared plus a dx. We're going to do this by trig substitution. And once I get doing with this, you're going to do integrals that look like that. No matter what number a it is, just going to write the answer down without even thinking about it. Because this is a plus sign, this whole thing is the hypotenuse. So up here we have x squared plus a, and the other sides then are x and square root of a. That's how Pythagoras works. Now, opposite over adjacent is tangent, so square root of a, tangent theta is equal to x. Hypotenuse over adjacent is the secant, so the square root of a times secant theta is equal to the square root of x squared plus a. And we need a dx, so we derivative. So we have dx is equal to, and what's the derivative of tangent? The derivative of tangent.
Secant squared?
Yep. So this becomes square root of a, secant squared theta, d theta. There's a trig sub problem. So this integral now becomes, well, on the bottom, so here's the square root of the bottom here. So we have to square both sides, and that gives me a times secant squared theta. And then we replace the dx by all of this. That gives me square root of a, secant squared theta, and then d theta. And I'm going to pause there for a minute. Anybody got questions about anything yet? So once I'm done with this, you never have to do an integral that looks like this again. You just write the answer down. Questions on anything I've done there? And I'm also stuffing my face with French fries. I timed my oven wrong. I was hoping to have them done before you all got here, but oh well. Okay, now the secant squareds cancel out. And the square root of a over a reduces to 1 over the square root of a. The secant squareds, they cancel out and just leaves me with d theta. So this is a constant. What's the integral of 1 d theta?
Theta.
Yep. So this turns into 1 over the square root of a theta. And now we solve for theta. And I'm going to put the square root of a back over here. The tangent is this over this. To get theta by itself, you do the arctangent of both sides. Tangent of x over square root of a. And every integral that looks like this has an answer that looks like this. So no more doing those integrals, just look and see them. And I'll give you an example right now. All about being lazy. So if we have the integral of 1 over x squared plus 9 dx, that answer is 1 over 3 arctangent of x over 3. See how you do it just by looking. That's the answer to all of them.
That's kind of awesome.
We have the integral of 5 over x squared plus 7 dx. Well, that 5 is just a constant. It can come out. And so the answer will be 5 times 1 over the square root of 7 arctangent of x over square root of 7. That's all there is to it. If it looks like this, the answer is that. You don't have to go through doing all the trig sub or anything like that. That's going to make these less painful. Question on what I did there? Okay. Let's do a couple of examples. And that will finish, tonight we'll finish partial fractions. If we were actually in a classroom like the ancient times, what we did last time and this time I would have done all in one classroom, but we're not in a classroom, so I'm kind of breaking it up in two so you have time to think about it a little bit. All right, so here's our first example. The integral of 2x plus 1, is that the one I wanted? Yeah. Over x squared times x squared plus 8 x. All right. Now, here we have repeated linear. X squared is linear, is x to the first times x to the first. So these are both linear and they're repeated. That's why we have a 2. And here, plus 8, this makes this an irreducible quadratic. So we have 3 factors in the bottom. So this integral is going to break up into 3 pieces. We'll have a over x plus b over x squared plus, I'm running out of room, and over here, cx plus d, and all of that x. So that's how it breaks up. I'm just going to pause there while you write it or look at it or think about it. I have another couple French fries in my mouth. Questions about the setup?
Wait, why is the like under b is x squared?
Because let me just do something different here. Hang on, and I'll show you why. if I want to break this fraction down into all of its possible parts, all possible parts, I would have a over x plus b over x plus squared plus c over x cubed. What's the so looking over here, what's the common denominator of those three fractions? What's the common denominator over here?
X.
Not just x. We got x to the first, x to the second, x to the third. In order to add these together, we need a common denominator, which is?
X cubed.
X to the third.
Yeah, x cubed is the common denominator. So this fraction could be broken down into three parts. So here, so c can't be 0. If c is 0, we don't have a common denominator of x cubed. b could be 0. The common denominator of those two fractions is x cubed. A could be 0. The common denominator of those is x cubed. So when we break our fraction into its parts, we decompose it, we have to allow for every possible kind of part. So I think that was Mikhail. Does that kind of answer why I did that?
Yeah, I think so. Thank you.
There was like one or two of these in the homework or something, but I'm glad you asked that. All right. Okay. Oh, geez, I don't even know what that is. X squared, I'm reaching too far. X squared plus 8. There. Now, when we're done with this, it's possible that a could be 0. If a is 0 and I don't have that, this is still the common denominator of those two. B can't be 0. C could be 0. D could be 0, but they can't both be 0. So there's where we are. Now, our job is to find A, B, C, and D. So like before, I'm going to multiply everything by the common denominator. That leaves us with 2x plus 1 is equal to a times x squared plus 8 plus b times x squared plus 8. Oh, I'm running out of room. I have to rewrite that. Hang on. 1, a times x times x squared plus 8 plus cx, oh crap, cx plus d times x squared. So when you multiply everything by the LCD all the way across, this is what you're left with. I'll pause there for a minute. If anybody's got questions, good thing I'm recording this. You can go back and look at it and hit your own pause button. So questions on that? Now, for the homework from last time, you could do the shortcut method. You could pick X values that makes things disappear, but we can't do that this time. There's no X value I can put here that's going to make this equal to 0 because it's plus 8. X squared would have to be negative 8 to make this equal to 0. So we can't do that. So the next thing we have to do, there's no shortcut, we have to multiply all of this out. So if I didn't make a mistake, I multiplied everything out. So double check me on that.
You good?
Okay, thank you. It's the little things I sort of always mess up a little bit. All right. Now, I'm going to use the fact that addition is commutative. 7 plus 9 is equal to 9 plus 7. So I'm going to rearrange all of these and bring things together. As soon as I find my colored markers, hold on. Got too much stuff in front of me here. And, there we are. All right. Here's an x cubed, and here's an x cubed. So I'm going to pull those out in front. And factor out the x cubed. Here is an x squared, and here is an x squared. So I'm going to pull that out. All I'm doing is rearranging this so it's a little more orderly and a little more neat. Here is an x to the first term, and it's the only one there. It's the only one that we have there. Hold on a minute. Get plus, and that gives me 8ax. And lastly, we have this right here. We have a constant term. So I multiplied everything out, and then I just took this and rearranged it. So we have x cubed, x squared, x to the first, constant. I just made it look a little more neat. I'll let you get caught up for a second. Everybody all right? No. In fact, because last time I used an expression equating coefficients, looking from side to side. So I want to have all the terms in descending order. It would be legal to pull out the 8, but it would make it more confusing. All right, now we do this. Oops. All right, so now we do equating coefficients. I lost something here. So looking from side to side. This is the only term over here that doesn't have an x in it. This is the constant term. And over here, I have a +1. So because of the equal sign, these two have to be equal. So from here, we see that 8b has to equal 1. So that means that 1 over 8 is equal to b. So now we found what b is. Looking over here again, this, oh, that should be a 2, hang on. This is the term that has x to the first. Over here is an x to the first. This has a 2 in front of it. So these two have to be the same. So here we have 8a has to equal 2. And that means that a is equal to 1 over 4. So now we have a and b. Everybody okay? You do a couple of these, you'll get very quick at it, even though it might seem kind of overwhelming right now. All right. We still have to find c and d. One of those could be 0 or not. So looking over here, here's x squared. There is no x squared over here. So you can think over here, there's an x squared with a 0 in front. It says there is no x squared. B plus d has to equal 0 because there's no x squared over here. So we see that b plus d has to equal 0. But I know what b is. B is 1/8. So that means that d has to equal negative 1/8. In our last term here, we have the x cubed terms. There is no x cubed over here. There are 0 x cubed. So a plus c also has to equal 0. I know that a is 1/4. That means c. That means c has to equal negative 1/4. And now we have A, B, C, and D. So these problems are more algebra than calculus. So anybody got a question here? Okay, I'm going to write these over here so I don't forget them. A is 1/4. B is 1/8. C is negative 1/4. And D is negative 1/8. Okay, so there's our coefficients. Get rid of all of this. Okay, I'm going to get rid of this. I need some room. So here's what this becomes. A is 1/4. Whoops. So A is 1/4. So that gives me 1/4 the integral of 1 over x dx. B is 1/8. So we get plus 1/8 the integral of 1 over x squared dx. C is negative 1/4. So we get negative 1/4 the integral of x over x squared plus 8 dx. D is negative 1/8. So we get negative 1/8 the integral of 1 over x squared plus 8 dx. And there's the 4 integrals. These are constants, so you can just pull them out in front. So I broke that up into 4 separate integrals. And again, I'm going to hold back in case you got a question. Just doing a couple of these tonight, and that takes us to the end of this.
Is the denominator for the last integral x squared plus 8? I just can't see it.
Oh, it is, but I wrote D. I don't know why I wrote D. Is that better?
Thank you.
Yeah, my handwriting. All right. Well, what's the integral of 1 over x?
Ln x.
So we get 1/4 ln of x. Over here, let me rewrite this so it looks better. So here we have 1 over x squared, but that integral can be written as, instead of 1 over x squared, write it as x to the negative 2, and then just integrate it with the power rule, add 1 to the exponent, and divide by the new exponent, we get negative 1/8. So that takes care of that integral. Here we have x on the top, x squared on the bottom, plus 8. So what method are we going to use for this one? That's right out of Calc 1.
U substitution?
That's a U substitution, and the 8 has absolutely no effect on them. This could be an 8. This could be a... Oh, wait a minute. I'm sorry. Yeah, this could be an 8. This could be a 10. It could be a 15. It could be anything. So when we do that U substitution, there's a 1/2 that's going to come out. 1/4 times 1/2 is 1/8. And then we will get the ln of x squared plus 8. So anytime you have something that looks like this, doesn't matter what that constant is at all. This integral will always be this. You just look at it and write it. Doesn't matter what the constant is. That doesn't affect it. And the last one here, I'm running out of room. Just like we did before, I need a bigger whiteboard. So this integral, I'm going to pull down over here so you can see it. Negative 1/8. And just like we did before, 1 over the square root of 8, arctangent of x over square root of 8, and then plus c. And that problem's all done. So the integrals, when you're doing partial fraction, they're going to be ln's, or they're going to be something like this, a u sub or an arctangent. And it's going to be the same structure every single time.
I'm sorry, does that say 1 over square root of 8 arctangent and then x over square root of 8?
Yeah. Yeah, it does. Yeah. Boy, that's kind of messy. Then I'm trying to make the next one neater because I ran out of room over here. So about the arctangent, let me just remind you again of what we did a little bit earlier. If you have an integral that looks like this, plus, I don't know, what's a? And k is just a constant. Every single time, it's going to be k, the constant, times 1 over the square root of a, arctangent of x over the square root of a, plus c. So it's just look and do. You don't even have to think about it. If in your book you look at the list of basic integrals, you'll find this formula in here, and it's going to look just like that. So it's kind of nice. You just don't have to do the integration at all, even though they look messy. And tonight, this is the end of integration techniques. This is as far as we're going to go. There's lots of other ones, but if you can figure these out, you can figure those out if you run into them anywhere, and you won't. So do another example or two, and that's it for tonight. And then after this, we have 2 more sections of chapter 8 to do, and I'll get to that in a minute. So the next 2 sections don't have different kinds of integral. There's something we do with familiar integrals, but I'll get to that in just a minute. So let's try another example here. Let's try, let's see here, the integral of x over x plus 1 times x squared plus, I don't know, x squared plus 9 dx. All right, in the denominator, we have 2 factors. We have a linear factor, and we have an irreducible quadratic factor. So this integral breaks up like this. We have a over x plus 1 plus bx plus c over x squared plus 9, and all of that dx. And if I had another factor here like x plus 3, there'd be a fraction over here with x plus 3 in the bottom, but we're not getting crazy with this. It's not about doing long, complicated problems. It's just like showing you the process with when you have rational functions, a polynomial, because they come up a lot. As I mentioned before, if you're going into differential equations, you're going to see things like this, but in a whole different universe, something called a Laplace transform. And partial fractions is the cornerstone to solving those. All right, so we have to figure out A, B, and C. Now, A cannot be 0 because we have one of these here. B could be 0, maybe, may not. C could be 0, maybe, maybe not. They just can't both be 0. And that will all happen when we do this. So we multiply everything by the LCD. That gives us x is equal to a times x squared plus 9 plus bx plus c times x plus 1. And parentheses there are crucial. So we okay? Now, I can't pick an x value that makes a disappear. So we need to multiply everything out, not a shortcut method here. So we get ax squared plus 9a plus bx squared plus bx plus cx plus c. So I multiplied everything out. And now I'm just going to rearrange things so that it's more orderly looking. All right. We have two terms that have x squared in it. So we put those together. I'm just rearranging these and then doing a little bit of factoring. We have, oh, there it is. Bigger whiteboard, I need a bigger table also. We have two terms that have x to the first. So we'll put these over here. And we have two terms that are constant terms. So I'll put those at the end. 9a plus c. There. Looks a little neater, looks a little more orderly. Question yet? Okay. I can get rid of all this, and reminder, this is being recorded. Okay, now, what's the constant over here on this side of the equation? What's the constant?
0.
Yep, there is no constant, right? 0. So this has to be 0. So 9a plus c has to equal 0 because there's no constant. Well, there's a constant of 0 over here. Here's an x to the first. The coefficient is a 1. Here's an x to the first. Here's the coefficient. Because they're equal, b plus c has to equal 1. If this was a 5, it would be b plus c equals 5. If this was -3, it'd be b plus c equals -3. And finally, so that takes care of that, that takes care of that. Now, here we have an x squared. We don't have an x squared over here. So a plus b has to be 0 because there is no x squared over here. Got questions? Takes practice. Well, all of chapter 8 takes practice. All right, so now we got to figure these out. Wow. Well, let's see. What are we going to do here? So you may have seen problems like these somewhere in your past. Well, from this, I know that A is equal to -b. So I get that right away. I don't know if that's going to help me. Oh, that might help me. And so -a is equal to +b. So here I have an equation with a b and a c. Here I have an equation with an a and a c. But I can replace this a by -b. So I'm going to do that. So we're going to put this negative b. I'm going to put that right there. So now we get negative 9b plus c is equal to 0. And I know that b plus c is equal to 1. And that might look familiar from maybe high school or something when you did 2 equations and 2 unknowns. How can we solve that?
Systems of equations,
I couldn't hear that quite right. What?
like where you like add it down, but first you have to like have the c's cancel out, so like multiply one of the terms by -1.
Yep. So I can do anything I want to this as long as I do it to both sides. So I'm going to multiply everything here by -1. So that's going to give me negative 9b plus c is equal to 0. And it's going to give me negative b minus c is equal to 1. No, just a little example. 3 plus 5 is equal to 8. Well, let me do it on another board. So what we're going to do is add those equations together. And this is as bad as these are going to get. We're not going to go crazy with algebra. It's not the point of this whole chapter. It's just about the thing here. So, true plus true is equal to true. Everybody agree with that? True plus true is true. That's something that comes up in discrete math, by the way. So let's have a true statement here. 3 plus 5 is equal to 8. That statement is true. 9 minus 6, I'm sorry, let's do it this way. 6 minus 9 is equal to -3. That's also true. So let's add them. 3 plus 6 is 9. 5 minus 9 is -4. And 8 minus 3 is 5. And that statement is also true. So true plus true is true. So we can do that with this thing. We can do that with this thing we have on the other side or the other board. So I multiplied this to get negative. So if we add these, -9 of something, take away 1, we get -10b. C minus c is 0, so we get 1. So now we know that b is equal to -1/10.
Shouldn't negative b minus c equal -1?
Oh, -1. Oh my goodness. Thank you so much. Was that Lauren?
Yes.
Oh, thank you so much. Oh, geez. There we go. It's kind of dumb stuff I do all the time. That's what makes grading tests fun. That's a sort of a dumb mistake, easy to do. So if you were to do something like that on a test, I would think, oh, silly mistake, not really going to pay attention to it. But then I have to continue your problem as though the mistake was correct to see if you did anything else right. That's why it takes so long. That's why you need to write neatly when you do these things. Okay, so there's B. And then A is equal to -1/10. I've erased it here, but we knew that A plus B was equal to 0, so A has to be -1/10. And what does C equal? Well, C has to equal 9/10, because over here, before I multiplied by this, B plus C is equal to 1. So if B is 1/10, C is 9/10. And those are our coefficients for this problem. And thank you so much, Lauren, for catching that mistake. Boy, these problems are about as much fun as the weather outside right now, aren't they? All right, now we just put the numbers in. So we have the integral of a is -1/10. That gives me 1 over x plus 1 dx. That's this one. B is 1/10. That gives me the integral of x over x squared plus 9 dx. Oops. I'm breaking this in two. And the last part here, C is 9/10. So we get plus, we get plus 9/10 the integral of 1 over x squared plus 9 dx. And there's our three integrals. Now the easiest part of this whole problem is this. The integral of 1 over x plus 1 is the ln of x plus 1. Ooh, sorry. The integral of x squared over x over x squared plus 9, the 9 doesn't matter. This is a u sub, and we get 1/2 the ln of, I don't choke to death first, plus 9. And the last one, well, that's the arctangent. It's 1 over the square root of 9 arctangent of x over the square root of 9. And that problem is all done. The integration is the easiest part. All right.
That last one's over the square root of 9, right?
Square root of 9, yep.
Sure. Thank you.
I said it, but I didn't write it. Thank you, Jordan. When we come up to the chapter 8 test, just to give you an idea, one of your questions on the chapter 8 test is going to be an integral worked out from start to finish, just one problem. And your job will be, you're the person grading that problem. Is it right? Is it wrong? What's wrong with it? And if not, so I'm going to have you like check somebody's answer, not a real person, just have you check somebody's answer. All right, looks pretty ugly. That's an easy derivative to do, by the way. The derivative of this is this. The derivative of this is this. And the derivative of this is that. Oh, and I could, I could simplify this down. I could just make that 3 over 10. That would make it a little bit simpler. Can't take that 3 out, but I can pull this 3 out and it cancels with that 9. So not a lot of these in the homework I'm sending out tonight, but I'll probably make, yeah, so not a lot. I think 2 of the homework problems, in addition to this, there'll be some limits up here, like 1 to 3, and you just have to plug some numbers in there, but that's, you figure out how to do that. Any questions on this? So we have linear factors, repeated linear factors, irreducible quadratics. There is such a thing as irreducible, repeated irreducible quadratics. Not giving you those, that's just a bunch of nasty algebra and it takes away from the whole point of the integral problem on here. So you have a whole bunch of days until Tuesday to practice these. All right. So let me give you a preview of what's coming next week. Just a little preview. There's no new methods coming. Integrals are going to be pretty basic integrals, but there's a existential philosophical twist to what's happening. So let's take these 2 integrals. 1 over x dx and 1 over x squared dx. So the integral of 1 over x is
ln of x.
ln of x. All right. I'm not putting a plus c there because I'm going to do something else. And the integral of 1 over x squared, well, 1 over x squared is x to the minus 2. So this integral is 1 over x to the first when you do that integral. Okay, no big deal, right? Now suppose I put here 1 to 4. That would make this integral 1 to 4. This would give us the ln of 4 minus the ln of 1, which would just be the ln of 4 because ln of 1 is equal to 0. And that problem's done. If we go from 1 to 4 here, this integral from 1 to 4 would be negative 1/4 plus 1, which would be 3 over 4. So the answer to this definite integral is ln of 4. The answer to this definite integral is 3 over 4. That's Calc 1 stuff. Here's what's coming in Chapter 8. We have an infinity up there. We have an infinity. What the heck is infinity? Is not even a number. How can that show up on here? And what does that even mean? Let me show you what that means. So it gets a little philosophical from here. If we have the graph of 1 over x, but only in the first quadrant, so the graph of 1 over x kind of looks like that, right? And we went from 1 to 4. Well, 1 to 4. So let me do it that way. So that answer turned out to be, when we went to 1 to 4, this area, the area here equaled the ln of 4. Whoops, bad writing. Right? So for y equals 1 over x, the area under the graph, and the x-axis 1 to 4, that area is exactly ln of 4. Okay? Calc 1 stuff. But what we've done is we're not stopping. We're going all the way out to infinity. Does the graph of 1 over x ever touch the x-axis?
No.
No, it never touches. So what would your guess be for the area?
Infinity.
Yes.
You would think it would be infinity because there's a big leak over here, right? And similarly, if we have 1 over x squared, those graphs look similar, but it's much steeper. Well, it turns out, so if we go from 1 to infinity, it turns out the answer is not always infinity. This graph never touches the x-axis either, but it gets close enough and small enough, fast enough to essentially shut it off, even though it doesn't shut it off. So it turns out over here, you go to infinity here, there's infinite area. But if we go to infinity on this one, it actually adds up to exactly 1 square unit. So that kind of messes with the brain a little bit. So we're integrating from 1 all the way out to infinity on the number line. We're never stopping. The functions never actually touch the x-axis, but yet sometimes you'll have finite area and sometimes you won't. These are called improper integrals. Now, improper is a different meaning from improper fractions. This is an improper integral because we have a bound here that's not a number. It's a concept. So the last two parts of chapter 8 get into how this can happen. And that'll take us one or two classes on that a little bit with a little bit of philosophical stuff. And that'll take us to the end of chapter 8. So partial fractions is the last messy looking integrals that we do. Chapter 8, the integrals aren't very much. It's all about the infinity part up here. And that takes us, and then we also learned something called L'Hopital's rule, which some of you may have done in Calc 1, some of you didn't. So those are the last two topics of chapter 8. Chapter 9 is very abstract and philosophical. It's series and sequences. So how can you add up an infinite number of numbers and actually come up with a number? So when we did area under a curve, like in Calc 1, and you broke everything up into rectangles, you added up all the area of the rectangles to get it. But then at some point you had an infinite number of rectangles that all had area 0, and it magically added up to a number. So chapter 9 gets into how does that actually happen? It sort of gets philosophical. And the last part of this course will be parts of chapter 10, which will feel like a whole different course. So far, all of our functions have been on the XY axis, which is called rectangular coordinates. In chapter 10, we're going to transform them into polar coordinates, which some of you may have seen. So instead of a point on a graph being x comma y, it's going to be r comma theta, which is radius from the center and an angle. But we'll get to that in chapter 10. All right, a little preview here of coming attractions. So questions about anything? All right, so I guess enjoy this. It's going to be kind of stormy, I think, tomorrow. I think they're talking about maybe a first freeze tomorrow night, so it's also going to get colder. Good time to have a nice cup of hot something and do math, right? Well, all right, folks. If you don't have any questions, I'm good for tonight. Everybody all right? All right, send me an email. I will upload the recording and I'll put some of the homework up, and I'll see you back here on Tuesday.
Have a good weekend.
Bye, everybody. Thanks for catching